I'm going to kick it over to P-Dog77 and the Duke Zip.
Thank you. Good morning, DEF CON.
That is a lame round of applause. Cheer.
Good morning, DEF CON. Yeah. So welcome to our talk. It's on steganography and commonly used HF radio protocols. We have tons of content for 45 minutes. We've cut this talk about 1 million times. So we're going to jump right into it. First off, I'm P-Dog, Paul. When P-Dog is taken, like on Twitter, someone beats me to it, I'm P-Dog77. As a day job, I'm a security researcher at a startup called Confer Technologies, Inc. We're doing some cool stuff with endpoint security and threat sharing. So if that's interesting to you, please check us out, confer.net. But I mention that because this has nothing to do with my day job. It has to do with amateur radio. Amateur radio has been a hobby of mine since I was a little kid. Thanks, Dad. I'm now an extra class licensed ham, as well as an ARL volunteer examiner. We'll talk about that a little later. This is my second trip to DEF CON, so if there's any first-timers out in the audience, come on up here next time, please. And I'll turn it over to Brent.
Hey everybody, my name's Brent. I go by the Duke Zip on Freenode and Twitter. I actually don't work in the security industry whatsoever. I work as a software and systems engineer, specifically dealing with radio protocols and devices, but hacking all the things has been a passion of mine for way longer than that, so I love being here. I'm also an amateur radio operator since 2006, and I upgraded to my extra class last year at DEF CON actually, and I'm also a volunteer examiner. So, one very important warning, we're going to talk about hiding messages inside amateur radio communications. And we're going to talk about using cryptography layered on top of that. And we're releasing a tool that does all of this for you. This is completely against the FCC regulations as far as our interpretation goes. So we did not actually transmit any of this over the air, and we are not recommending that you do so either, okay? So, another warning, this was a project that kind of started as a fun conversation over drinks at a Massachusetts meetup called Mass Hackers. We are talking about cryptography. We believe that we're just using cryptography libraries, that we're just calling using the correct methods. But if you're trying to hide your stuff from 3-letter agencies, you probably want to audit the code. If you find something that we did incorrectly, we'd love to hear from you. You can let us know, and we'd be happy to fix it as well. So
what are we really talking about? We set out to demonstrate to ourselves and hopefully to you that it's somehow possible to create a really low infrastructure, fairly long range, covert, short message protocol that could be used in multiple ways, whether it was point-to-point, broadcast, or mesh. And for reasons we'll talk about pretty soon, we wanted to use common off-the-shelf consumer radio and computer equipment and some sort of commonly used digital communication mode that was already in use. Why would you want to do that? Well, the vast majority of us are probably dependent on some kind of short message communication all the time in our day-to-day lives, whether it's something like Twitter or SMS or whatnot. But all of those communication mechanisms are really dependent on some third party to provide the infrastructure, whether that's an ISP or a cell phone provider or someone actually building the platform on which we communicate. And those third parties don't always have our best interests at heart, right? So we could be subject to censorship or spying, or in extreme cases, these people want off switches on these communications, right? So mom and apple pie at DEF CON, I guess. We believe it's a fundamental human right to communicate without that form of interference. So that's why we're taking a look at this stuff, and one of the reasons why we think you should be interested as well. So you could use a method like this, hopefully to communicate in these ways. And we'll highlight some portions in the talk where relatively small changes to the things that we're doing could result in entirely new protocols. So you could definitely take forward this research and create something that's completely different, but along a similar line. If that doesn't motivate you, then likely there's probably bad actors doing something like this anyway. And I think it's important that we look at what is actually possible, what some of these communication mechanisms might look like, how we could find it, etc., so that we could combat really bad actors using techniques like this.
So Paul mentioned that we want to be able to have all these communications without the use of any infrastructure whatsoever. And that obviously includes the internet, which we're all very familiar with. It just so happens that amateur radio operators are complete experts in communicating worldwide without any infrastructure whatsoever. It is a really cool hobby, and you may hear us refer to it as both amateur radio and ham radio. The terms are kind of interchangeable. You get to do really cool stuff like transmit with up to 1,500 watts of power, which is a heck of a lot if you're not familiar with that. You get to do cool things like bounce signals off the moon, or bounce signals off the ionosphere over to the other side of the Earth, or practice sending a message to a satellite and having it repeated on the other side of the globe. So all kinds of really cool stuff you can do with amateur radio. One thing that is important to mention, so after we submitted this talk to DEF CON, this group calling themselves Lulz Labs released a tool called AirChat. And it's similar in some ways, but very different in other ways. It also uses encryption over amateur radio, but they're making absolutely no intention to hide that. They're basically just transmitting encryption. Anybody listening would know that, whereas we're doing steganography. Anybody listening should think that it's some innocuous, normal message that they would totally expect to hear, but buried inside it would be something completely different. So, you know, good steganography, good OPSEC. This is actually a picture from the TV show Lost, of which I was a huge fan of. And there was this number station on this island that continuously transmitted 4, 8, 15, 16, 23, 42. But number stations are a real thing. There are stations you can tune into on the shortwave radio, and there's some creepy music, and some person comes on the air and just starts reading off numbers. And 99.9% of the people in the world have no idea what they actually mean. We think that, or some people think that they may be, you know, secret instructions for spies across the world or something. But there's no, they're not trying to hide it. They're just sending numbers, and everybody knows it means something secret, and you don't know what it is. We're talking about doing things like having a radio in a pelican case, and you can run into the woods, throw an antenna up in a tree, and transmit your secret message, and then take it all down and run away. And if you're a receiver, you could have a 30 or 40 foot long antenna up in the rafters of your attic, and nobody would even know that you were listening in.
So how are we going to hide? We'll talk a little bit about the protocols that are used over amateur radio and HF radio for digital communications. These protocols are very much different than some of the traditional networking protocols we think of. In most cases, they don't have some of the features that we would typically look at to use as a covert channel. The protocols are extremely tight. The utilization of bandwidth and power is restricted because it's thought of as a hallmark of good amateur radio engineering, not to use any more spectrum than you need and not to use any more power than you need. So when you look at the design of these protocols, they're really designed in that way. So then you could look at maybe doing some sort of timing or substitution error, timing between symbols, or substituting one symbol for another, etc. But those are visible. And the more you use these protocols, the more you can actually stop seeing that stuff on the screen, and you can actually start to hear it with your ear. So we also took off the table what's termed spurious emissions, or adding additional tones or signals along with the transmitted signal. That is also against the rules, along with everything else that we're talking about. But it's extremely visible, and again, amateur radio operators have a tuned ear for that, and it's thought of as bad practice. So it's much more likely to get noticed. The candidate protocol for this really has to be in widespread use. It doesn't matter if you find an ideal protocol for embedding steganography. If you're the only person transmitting on that protocol, it's still a bit fishy, right? And then again, we really were looking for protocols that needed no special hardware or closed software. You can find great packet radio protocols, etc., but usually they require some sort of proprietary interface or software, etc. We were looking for something that you could do with standard radios and computer equipment. So predominantly we're talking about what in the amateur world is termed a sound card digital mode, or a mode that is modulated and demodulated with only a standard sound card and more or less a standard PC computer system. So the output and input of the sound card are wired to the microphone and output of the transceiver, and then somehow, usually through like a serial interface, you're keying the microphone on the transmitter. There are countless numbers of these protocols, anything from well-researched, well-designed, well-documented to something someone threw together in their garage. So if you're a protocols person, there's endless stuff to play with here. Go take a look. Some of the modes were developed specifically for this kind of use, but older modes, such as radio teletype, been in use for a very long time, have been adapted to being transmitted and received this way as well. But both the examples up here are very common protocols. They suffer from the problem that we were talking about before, which is they're very tight. There's almost no room to shove in any extra information here. The other thing to note about these protocols is they're more or less keyboard-to-keyboard chat. You can send freeform text, whatever you would like, during your transmit cycle, and then switch over, and then the other person talking to you does the same thing. So it's more or less a back-and-forth chat mode. So we need to find another protocol. Enter this protocol called JT65. It was developed by Joe Taylor in 2005 and originally detailed in a paper he wrote. It was designed for Earth-Moon-Earth communications, or bouncing signals off the moon and returning them to Earth. It's a really long, lossy path, of course. So this protocol has some error correction built into it. It's extremely power efficient. With about 25 watts of power on a good day with decent conditions, you can communicate worldwide on JT65. It's kind of in between a chat, keyboard-to-keyboard chat protocol and some of the more packet protocols. We'll talk a little bit about the structure. It has an extremely low data rate. That was one of the trade-offs here. All of this is a trade-off, right? For more privacy in the communications, we are trading a lot of bandwidth, as you'll see. Good news, it's an open source implementation. It is in Fortran, and the error correction code is in C. So we did deal with the Fortran code because we wanted to stick as close to the original implementation as possible. So what does a JT65 communication look like? This is a screenshot of one of the more common clients that is in use. Basically, amateur radio operators use this protocol to exchange a few little bits of information that compose a communication. The amateur radio call signs, the 4-digit grid locator in a system that is detailed in our bibliography notes, as well as a signal report, how well one side is receiving the other communication. It's sort of a time-dependent mode. Transmissions begin at the top of a minute and are around 47 seconds long with about 13 seconds of silence, so it requires some relative clock synchronization between the receiver and the transmitter. When they're used on HF frequencies, generally hams congregate around these watering hole frequencies, which are displayed on the slides. And for radio folks in the room, it's upper sideband AM. So you're getting about 3,000 hertz of usable passband there, and multiple JT65 conversations will happen within that pass. And you can see on the waterfall display up there, there's one that's fairly strong, kind of to the left, around 500 hertz. So let's talk about how this protocol actually works, because we need to understand that so we know how we can hide in it. Here's one of those structured messages that I talked about. It's 2 amateur radio call signs and the grid locator. Hopefully these are still not somebody's real call signs. If they are, we're sorry. The protocol puts that message through a custom packing routine that understands or has lookup tables for the structured pieces of an amateur call sign, the prefix, the suffix, pieces of that grid locator, etc. And you get out a 72-bit message. It's shown here as 12 6-bit symbols, and it's usually manipulated in those 12 6-bit symbols. Remember, we have a 1-minute transmit time, and we're talking about 72 bits, so you can do the math. We're not talking about streaming HD video. That's the source encoding, and then it goes through a very important step. It's transformed into a 63-symbol message through Reed-Solomon error correcting encoder. Sorry. And then the resulting symbols go through a series of shuffling operations and interleaving operations, as well as a gray coding, to result in 63 more symbols, which are the final symbols. In the original paper, Joe Taylor says that some of these steps were done to improve the error correction capability of the protocol. From here, it's modulated into audio, and we'll talk about how that happens. So you have these symbols here, which are shown as just regular numbers. Those numbers are then put through this formula. So JT65 is an MFSK, multiple frequency shift keying protocol. And you can see the formula there, do the math. You put in a number, you get out its own. 1 second. These guys are coming up here. The actual packet, and that's our term, I don't know if it's really used out there, is 126 slices. A full half of the packet is a synchronization tone that the demodulator uses to find these signals and find the relative value of each symbol value there. So that's how it is transmitted on the air. That sync tone becomes really, really perceptible to your ear, and you almost start singing it to yourself. This is the alien music that we had talked about, and you'll hear some of it later. You start singing it to yourself when you work on a long project with it. How are we going to hide and read Solomon codes? We're going to shove in some errors. I'll cut some time off this slide so we can do this. And we did it in multiple ways throughout the process of the project. In the end, and what we're going to talk about is we're basically going to encrypt and pack our own custom message and apply forward error correction on top of that. Basically a truncated version of the same Reed-Solomon code that's used in JT65. Reed-Solomon codes are everywhere. There's prior work in steganography in Reed-Solomon codes, so if you want to hide information in Reed-Solomon codes, look at that paper.
Pardon the interruption. We have a little tradition here at DEF CON for first-time speakers. It's really hard to get accepted, and these guys did it, so give them a round of applause, please. Thank you. Oh, you got one. Cheers.
You forgot to mention it's a brand new tradition.
Oh, yes, it's a brand new tradition, never before done. As you were. I'd like to see you say MFC Protocol 1836-2 now.
I'm transferring the mic over to Brent.
All right, so how are we actually going to encode the steganography? That's the fun part, right? Let's say we have a message we want to hide inside of our JT65. Let's say we want to hide DEF CON 22, right? We're going to put it through that same source encoding step that JT65 uses and convert it into 12 6-bit symbols. And we're actually going to add an additional 8 symbols, putting it through a forward error correction algorithm, the same one JT65 uses. We're not going to make it quite as big, but we're going to add a little bit so you can tolerate some errors from interference or from whatever inside your transmission. This will allow us to tolerate up to 4 errors in the steganography portion of the message. Now, we also have to pick places that we're going to stick this in the message. So we allow the user to input a key that the receiver would also have to have knowledge of. And we'll generate, we'll take the SHA-512 hash and generate 20 locations for that. Now, there's 63 possible locations. So we'll take the bytes of the hash and modulo by 63. That'll give us all those numbers, but of course we'll have a few leftovers because 256 is not divisible evenly by 63. So for the numbers 252 through 255, we'll just throw those out so we don't have an uneven bias towards the symbols 0 through 3. So it'll all work out in the end, we promise you.
It made sense at 4 a.m.
It made sense at 4 a.m., right? For this example, for the key PDOG, the Duke zip, these are the 20 locations that you would get out of that method. So we could take some innocuous message, the 2 call signs and the grid locator that we showed before. This is the 63 symbols that would get transmitted over the air. We'll take our steganography, the 20 symbols with the error correction, and the 20 locations that are generated from the hash of that key. And we'll start with the first byte. In location number 9, we'll replace that with a 24. In location number 29, we'll replace that with a 42. And you just go through all 20 symbols, and what you end up with is the original message on the top and the new message on the bottom that can be recovered both into the innocuous message, and if you know the key and can reorder those symbols in the correct order and know where they're located from that key, you'll be able to get the steganographic message as well. And this also can tolerate additional errors in the transmission, so this will go a long distance, and if you pick up interference, you'll still be able to get both messages out of it. But we wanted to do encryption too, right? We like encryption, yes? All right. So there's 12 6-bit symbols, which gives us 72 bits, and most of the encryption standards I know use 8-bit bytes. So if you divide 72 by 8, you get exactly 9 bytes, which is an absolutely amazing coincidence, and we love that fact. And this guy does too. So what we did was we created what we call a packing function, where you have the 9 8-bit bytes that you can fit, and you would convert that just by chopping them up into 6-bit symbols. There's really no magic here. We decided to do it where you have 8 data bytes for the encrypted data, and a 1 byte, we call it a status. You could think of it as a header. And why would you want to have a header in this message? Well, we thought it would be cool if you had a really long message that would take multiple transmissions to get across. It would be really neat if the receiver could see, you've received packet 1 of 3, you've received packet 2 of 3, and then when you get the third one, the whole thing decodes for you. You can just reassemble the whole thing. So we're basically using it to keep track of packet numbers for reassembly. In the case of a stream cipher, if you just look at the bottom diagram, it's probably the least complicated part of the slide. The first bit is a flag for the first packet. The second bit is a flag for the last packet. And then the remaining 6 bits get used either for the total number of packets, the packet number, or because we have a stream cipher, we need to track how many bytes are actually used in the last transmission. In the case of a block cipher, it's a little bit simpler. So you just have that flag for the first packet, and then you have 7 bits to track the packet number. Now this does give us the limitation of one message, if you want to call it that, would be limited to 1 kilobyte of data. But if you had more than that, you could just do multiple longer transmissions and reassemble them at the end. It's not really a limitation. It just looked cool on the slide at 4 a.m. So yeah, we went through all this and we had a problem. And we'll talk about some statistical analysis we did on this data. But what we found by doing this was it was really trivial to pick out the steganographic messages because the way that whole status byte worked, you would end up with the symbol number 32 way more than any other symbol. It just kind of was very, very obvious if you knew what to look for. So what we did was we came up with something cool that we're calling the bit swapping.
Or the bit magic.
Or we affectionately call in IRC the bit magic at first. You take the 8 bits of the status byte and you swap them with 1 bit each of the 8 data bytes. And this particular diagram may not give you a warm fuzzy feeling because it actually forms a pattern in those data bytes of which bit you're swapping out. But the reason for this is when you convert it, convert it to the 6-bit symbols, it actually more evenly distributes the bits amongst all of those different symbols in all of the bit locations. So doing some statistical analysis on this, in the end, it actually comes out very much flatter distribution. It looks good to us. So the tool we're releasing and we're going to demonstrate for you is kind of a multi-layered software application. The bottom layer, the base layer, is just built off of the original Fortran source code and C source code from JT65 protocol. And we've just compiled that with F to Pi to make it really accessible from Python. And the C code is just a binary that we can call. On top of that, we made it even easier to access with a wrapper layer that's in Python. And then for our libraries, there's actually 2. JT65 Stego. This is where all of your encryption, all of your ciphers, all of your steganography that you can call is in this library. And the JT65 Sound, which is a Python library for all of your audio encoding and decoding. So using all of those layers, you could create your own tool to basically do this however you wanted. We have a proof of concept tool we've released, JT65 tool, and the analysis package, which we'll also talk about, JT65 analysis. And if you really want to mess around with the protocol and change some things around and experiment and see how you could make yours different, this all comes with unit tests and black box tests, so you can make sure that if your experiment doesn't break anything. So play with that if you want to. If not, we did it for fun. So this is where I demo the tool.
And we hope the AV doesn't blow up.
We hope the AV does not blow up. You can see that, right? Okay. So what we'll do first is I'll just show you the help output from the tool. There's 2 basic functions, encode and decode. There's a whole bunch of different options here. You can inject additional noise if you really want to try to hide where your message is embedded. An interactive mode for listening to messages live on the air. Places to embed your messages. The JT65 protocol, if you look into it more, there's all kinds of options like a frequency, a base frequency, and a mode. For examples for ciphers and encryption, that we just wanted to show you how they would work. We have super secure stuff like XOR. Okay, got a laugh, good. All the way up to real things that might be secure like GPG and one-time pad. So there's trade-offs with using all of these, and as you think about it, you'll figure out what they are. But we've shown them all as examples here, so do with them what you will. For the output, you can print the symbols out to the terminal or out to a WAV file that you could broadcast over the air, but we did not. Or for the input, the same thing. You can take the symbols from standard in or read in from a WAV file. So let me show you what happens when you encode a message here. It's cutting me off. Okay. Let me run it then. So what you can, how about that? What you can see here is we've encoded this message. The innocuous message is 2 call signs plus a grid locator. Anybody listening to this would just see that on their tool. Our steg message is DEFCON 22. We're using that key from the example PDOG the DukeZip and just printing out the symbols to standard output. And you can see what symbols would get transmitted over the air. If you wanted to kind of follow along the different steps that this tool uses, you can enable verbose mode, where you see that source encoding step where you get 12 symbols, then you add in the forward error correction, the same thing with your steg message, and then the final output message is displayed here too. But the really cool stuff, of course, is the audio, which I know you all want to hear. So here we'll do the exact same message, but output to a WAV file. And I'll go ahead and play that WAV file for you.
Sing along.
Sing along. I love singing these things. After you've listened to them for 4 months every night, you'll love singing it too. Can you guys hear that?
Oh yeah, a little bit.
So we affectionately refer to this as the alien music because it sounds a little bit bizarre, especially when you're listening to the real airwaves and you've got multiple messages happening at the same time at like different bass frequencies, plus you've got all the static in the background and all the other noise. It just sounds really creepy. And we might have an example of that coming up as well. But I'll kill that. It goes on for a minute, but we want to do this as quickly as possible. So let me show you what happens if you run the actual tool, the most common tool that everyone uses to use this protocol, WSJTX. So if you were to open that WAV file or hear it over the airwaves, what you'll get is all you'll see is that innocuous message. You'll see the 2 call signs plus a grid locator. There's no other indication here that there were errors in the message or that there's like secret cryptographic data in there or anything like that. It's just nobody would be the wiser. But I'll close that out. Oops. I went past it. If you go to decode that file with our tool, you can see that this decodes both the original innocuous message and the steganographic message as well.
Whoa. So we wanted to play with this in some different form factors. One of the things that we sort of envisioned as we were working on this project was some sort of portable feed reader, and that led to this, which is a Raspberry Pi with a little TFT display on it. Can be run on batteries, obviously, and plugged into that, which is a pretty common shortwave receiver. You basically build a receiving station for this for under $200, run it on batteries. We were going to demo this here, but we're in RF hell in this room, and receiving those low power transmissions that we were just showing was not going to be quite possible. So videos or it didn't happen.
Well, it's the morning of June 14th, 2014.
It's like my confession with the time.
We're on my front porch here with a battery-powered Raspberry Pi, and that is connected to shortwave receiver.
You can hear those aliens.
Antenna.
That's just a wire in the tree.
21076. We're receiving some JT65 signals, and the Raspberry Pi is decoding, even though some of these signals are not audible to our ear over the static.
The laptop died. This is the part where the laptop dies? No.
Oh. You did kill the laptop. What did you do?
I didn't do anything, man. Anyway, since we're a little short on time, Brent's going to fix the laptop. And what I'm going to do is talk about some of the analysis that we worked on. I'm hoping I get an analysis slide. So we wanted to look at this protocol and basically figure out how would you locate if someone was going to do, if someone was doing these types of activities, if someone was generating fishy JT65 packets. If you've been paying attention, you obviously have some limited population of real JT65 messages in the universe, right? It's the structured communication that goes through a predictable error correction algorithm, et cetera, and then you're shoving a bunch of errors into it. The stock demodulator also gives you a lot of other statistics about the packet that's been received, one of which is a confidence value. That confidence value is essentially the demodulator as it bins signals into the various tones. It gives you back a 0 to 255 value, which is how sure it was that a given signal was correctly demodulated. So our thought process was you could take the numbers of errors that you had in a packet, and then some of these other things like signal to noise ratio or the confidences, et cetera, and do some sort of analysis and figure out whether a packet was suspect or fishy. There's some great pictures of this that we don't have right now, but there's an analysis tool or analysis section of our tool which will take in either a single JT65 packet or multiple, and it will produce graphic analysis of this for you, or it will output all of these statistics in basically a comma-separated values, and you could import them into whatever tool of your choice. So you can process these in bulk. We listened to probably around 3,000, we captured around 3,000 transmissions on 20 meters. Called those basically a population of natural packets, assuming that none of you had injected secret steganography on us. And then we generated 60 of our own stego packets, and through the patented JT65 crossover cable, which is basically a stereo audio cable, demodulated that on the bench. And what we found was that when you look at that ideal scenario where you have a lot of packets that were received over the air and just a few that were generated with the stego tool, and you had a clean transmission line between the two of them, these packets were extremely obvious. And Brent's going to bring me to that slide right now, please. Woo! Thank you, Brent. You should always co-present, and you should always have a backup laptop.
Get him another drink.
Yeah. Get Brent another drink. Yeah, get me there. Yeah, that's good. So the analysis module, yes, graphics and pictures, and you can see those things. So we thought finding steganography is pretty easy, right? Here's the pictures that I was talking about. On the upper left-hand side, that's the population of natural packets. On the right-hand side, you can see the orange dots. Those are our stego packets. This graph is numbers of errors in the packet on the x-axis and the standard deviation of that confidence value across those errors on the y-axis. You'll notice this is the really non-populated area of the graph that you see in the natural packets, and then all of our stego packets show up there when we did it on the lab bench. It's because you're essentially taking these low error rate packets and you're shoving a bunch of additional errors into them, and they more or less slide into this place where it's really obvious that they exist. So I closed the laptop, I was done, I had a drink, it's finished. Brent says, well, it's probably not that easy, Paul, because you're not taking into account any of the interference that would be normally received over the air. You're not taking into account weather interference, bad transmitters, et cetera, et cetera, et cetera, et cetera. Transmits on top of each other are really problematic in this protocol. So what would happen if you actually, again, because we can't send these packets legally, what would happen if you actually simulated that behavior? If you took the real error values and the real signal to noise values, et cetera, out of these packets that are on that left-hand side of the graph, and you substituted them into your stego packets, sort of pretending you received those stego packets over the air. So the tool supports that too. You can take a population of real-world packets and model your stego packets against them, right? And in that case, not so much. The same measurement value. It turns out that there is a lot of error that you get on these transmissions in the real world. So it's not that simple. I'll try to switch mics. We tried other measurements, signal to noise ratio, not quite. I'm not a statistician. You probably have detected that already, and there was already enough math here to make my brain hurt. There are some statistical methods that we think could tease out a few of these packets. For example, you can see we can get some out here, but still not all of them. So it's actually a little bit harder for the amateur hobbyist, non-professional to detect than we thought. We did observe some interesting patterns. This is the frequency of error symbols and the error location and the location of those error symbols that we've seen in the real population of packets. This was about 14,000 packets received at various intervals over a couple weeks. And you can see they're definitely not random when you look at the real world. What symbols happen as errors in the real world and what symbol error locations show up in the real world. We didn't make any attempt to emulate this behavior in our tool or in our distribution, so it's probably something to be aware of. If you were going to use a method like this, absolutely take into account what happens in the real world. We don't really know why this is ourselves, but we have some theories. And on the bottom, you'll see two pictures. Those are 200 Stego packets, basically the same message, encrypted and encoded with the same key. And you'll see that the locations and symbols really show up as very unnatural peaks there. So that's certainly an issue. What about distance? We also decided we couldn't send the packets and fly around the world trying to receive them. No one would pay for that either, let alone the fact that it would cause us a problem. So our theoretical maximum number of errors we could decode is 10. We could theoretically have 10 errors across the packet when we're done, and we could still decode the actual JT65 and our encoded message. That's a absolute best case scenario. Turns out more likely 6 or 7 or so we could tolerate. So what we did was, out of our large population of packets, we looked at how far away the sender claimed to be from the receiver, and the receiver was that wire antenna in my attic. And they were out over 1,000 miles, maybe several thousand miles, couple thousand miles. So it's definitely possible that something like this could be a worldwide short messaging protocol, either if A, conditions were perfect, or you had repeating stations. Obviously, there's vulnerabilities and known limitations to this. We've made a lot of trade-offs. We understand that. Analysis and detection is definitely a problem. We talked about what hobbyists can do essentially with the stock tools on a bench. If your adversary is much differently equipped than that, you might have a different problem. Transmitter location is also a problem. There was a talk yesterday on fox hunting, and they do fox hunting here. This is a well understood problem in game, especially by the 3-letter agencies. And we certainly think that if you could observe transmitters from multiple locations, you would be able to better tease out what the error symbols that were injected are. Except for the GPG mode, we're not doing anything with signing these transmissions, so there's a message forgery problem. You could address that, but you're trading more bandwidth.
So how do you get this tool? We've been working on it in a private GitHub repo for many months, much longer than we probably ever thought we would. But this morning, right before we came on stage, we made that public. So it's on github/pdog/JT65stego. There is a version on the conference DVD as well. I would recommend pulling the GitHub version. We did make some performance modifications after we submitted the code for the DVD. But either one, they're both compatible with each other. They work great. So, we hope that we showed you how you can definitely embed hidden messages inside these digital protocols in amateur radio. If you don't want to do it the way we've done it, you can take some of the ideas and kind of pick your own protocol and kind of implement it in there. So, lots of different ways you can hide these things. We only started to scratch the surface, basically. Some things we could do is keep looking into more ways you could detect this and work on how, counter detection, make sure that it's undetectable, working on the cryptography a little bit more, and looking into other protocols as well, as I mentioned. So, this is actually an older version of the presentation on the backup laptop, but there is a ham exam here if you want to get licensed in amateur radio this weekend at DEF CON. On Sunday in the Crypto and Privacy Village, you can head on down there at noontime and take the test. And if you're not familiar with the material, but you really want to get into it, there is a cram session at 9 a.m. in the Wireless Village, which is listed there. And if you see the people, we had pictures, but this one doesn't have it. If you see the people with these light up badges here, those are all of the volunteers that are going to be helping to administer the exam. And if you do pass any level of the test, there's 3 levels, you'll be going home with a really cool medallion that is somewhat like this. They're pretty awesome. So hopefully come by and check that out for sure. I hope to see you there.
But don't do any of this.
Right.
And this is actually on the test, so we've given you several answers. Don't do any of this.
Is the person who organized the exams in the room? Does he want me to mention him or give us a wave, or he can be humble and...
I can't see anything.
I can't see anything.
Oh.
There he is. K3QB is the organizer of that. So we want to thank everybody in the room for coming to see this. We're kind of running up on the edge of time. We especially want to thank lots of people from Massachusetts group, Mass Hackers. We do have time for questions. Okay. We want to thank everybody from Mass Hackers. They've heard various iterations of portions of this talk, or we bounced ideas off of them as well. So it does look like we have time for a few questions, if there are any. Yes, right over here. Your hand was up first.
Yeah, I can repeat it if you want.
Okay, go ahead. Yeah.
So the question is really around the time synchronization, and especially when we're talking about mobile scenarios that might not have access to a network or whatever to synchronize. Yes, GPS was the option. That would be one option. If you could receive a time source from somewhere that was reliable, you could definitely do that synchronization. The other option that I personally have thought about, what we didn't implement in the tool, is honestly, if you listen to one of these JT65 watering hole frequencies for long enough, you have a lot of transmissions that are starting when you basically want to start your transmission. And all I need is relative clock sync. I don't need specific. I don't need to know what time it is. I need to know when the beginning of a minute is. And yes, people are transmitting at the beginning of a minute. It is pretty exact. It's not 100% exact, frankly, if you listen to it, because what can happen is a transmitter can start transmitting before the start of the minute, and it can still be decoded because those symbols are missing in the transmission. But one of the thoughts that I had when I thought about that actually was you could always use receiving signals as a relative clock sync, and you could sync your signal to a signal that you received based on an offset. Oh, sorry. Did we look at having the data in the message and using the forward error correction to change that message into what we wanted to see? I'm not sure I totally understand. I mean, I think that there's probably various places you could actually do the steganography injection in that process, and there are various levels at that process that you could actually use as the we thought about, for example, using the real innocuous message as the key, so that you are actually transmitting a key along with it. Now that has problems as well, and an advantage it would be that you wouldn't have to necessarily know the key. You would just have to go through that algorithm. So there are probably multiple places where you could embed the stego. There are probably multiple other facets of this protocol or another one that you could exploit in that way. Yeah, you're good. I think that's good.
I think we have time for one more. Okay, so the question was, if you remove the cryptography, would it still violate the FCC regulations?
Yeah, I'll just go back to this level.
I'll take that one. So, you could talk to a lawyer. We're not lawyers, first of all. Our personal interpretation is that you cannot hide a message inside of a transmission. So, for us, hiding it without the encryption would still count. Now, there may be other people that have a different interpretation of that, and I know some of them are in the room actually. They actually may know more than I do because they are both hams and lawyers. So that's a good question for them. There are some exceptions to using encryption. You can talk to if you're sending commands to a space station, there is a workaround for that, but we obviously are not doing that. Somebody mentioned to me 2 days ago that if you're controlling an RC aircraft and it's sending back telemetry data, that is also allowed. But aside from that, don't quote us on that, but just don't do it. If we're not saying you should do it, okay? Right. I think we're out of time, but we'd be happy to answer more questions outside. We'll probably be at BarCon after this. If you see us around the conference at any time, we'd love to talk about amateur radio, this talk, or pretty much anything whatsoever, like puppies. So thank you very much for coming. Thank you.